Welcome to the king of functional groups in infrared spectroscopy, and that's the carbonyl group. I told you it was important, and we're going to see that it's a very clear, very strong signal, and the functional groups that contain carbonyls can be easily identified using the hints that IR spectroscopy gives us. So, let's start exploring. So the carbonyl peak comes out around 1700 wave numbers. So whenever we see a really strong peak around 1700 wave numbers, you just might have a carbonyl compound. Now, carbonyl containing compounds can be easily interconverted between each other using the methods of organic chemistry. You should be able to look at these reactions and come up with a set of reaction conditions that would affect each one of these transformations. So review your organic chemistry. Now is an excellent time to review synthetic chemistry and functional group transformations with carbonyl chemistry. Do you know how to turn, say, a carboxylic acid into an acyl chloride? And if you can do that, you can easily make an amide or an ester. Of course, you can make an ester directly from a carboxylic acid. Do you know how to do that? Do you know the trick for making converting a ester into a ketone? Don't just use a Grignard reagent. You'll have to be just a little trickier than that. So, review your organic chemistry. These are things that you'll need to know, and it will help you interpret some of the reaction examples that we're using Spectra to interpret later on in the course. You should also be able to name all of those functional groups. So if you can't, be sure to review your organic chemistry. Now, let us compare the double bond, the alkene double bond, with the double bond in the carbonyl double bond. So there's a carbonyl double bond, and here is an alkene double bond. Now, of course, one thing that you'll notice for the alkene double bond, which we already know, is we expect to see the alkene CH stretch, and that's usually a well-separated, nicely defined peak above 3000 wave numbers. So there it is there, and of course it's not there because there is no CH2. Now for the carbonyl peak, we see this nice, strong carbonyl peak around 17, 15 wave numbers. We don't see it in this IR here because we see the carbon-carbon double bond stretch here. It's coming out a little under the carbon-oxygen double bond because the carbon-oxygen double bond actually has a higher force constant. The carbon-oxygen double bond is a little stiffer than the carbon-carbon double bond. Here we see some CH2 bending frequencies, and of course we don't see them here. We do see some carbon-carbon stretch bending frequencies, stretching frequencies on either side of the carbonyl group here, and we'll talk about that. So, as we might expect, the carbon-carbon double bond has a frequency of around 1650, and there's the frequency that we see for this ketone, around 1715, exactly where we expect ketones to be. So, we should be able to easily spot carbonyls because that peak comes out basically in this quiet area here. It's going to come up right here and be hard to miss. Now, compare this peak here with the other peaks. The other peaks seem almost as strong as the carbonyl peak, especially the CH peaks. Is that really real? Remember, most IRs you see are actually thin film casts on salt plates. And we have no idea how thick that film is. I mean, if one person makes that film twice as thick as another, they're going to have twice as much material the IR goes through. Now, if you make a solution in carbon tetrachloride or another solvent, you will know the concentration, and then you can control the concentration. You can make it more dilute to sort of see what the relative strengths of the signals are. Because one thing you'll notice is this is transmittance here. Now, 99% absorbance here, or 1% transmittance. What if I made this film just 10 times thicker? Well, then I would expect this to be 99.9% absorbed. But can you tell the difference between 99 and 99.9 on this? And that's the difference between 1-fold and 10-fold. Now, that's going to sort of really skew the relative intensities here. If everything's strong, if the film is really thick, everything's going to look strong. Compare that to this more dilute solution. Here, the carbonyl peak is definitely strong compared to the CH stretches and the other carbon-carbon stretches and heavy atom stretches here. So sometimes if you're having a little trouble interpreting what are my strong peaks, I don't know if that's a CO peak, it doesn't look very strong, or it looks strong but all the peaks look strong would be the question. If you go to a more dilute system, you might be able to spot the difference there. So remember, changing your technique, changing up your methods can be useful when you're trying to figure out what's going on. Now, here's basically why. If I had a compound at a particular concentration and it absorbed 10% of my IR radiation, what would happen if I made it 10 times as concentrated? That would be 10 times the absorbance. Well, if you do the math, it's going to lead to about a 66% absorbance of the signal, or really 34% transmittance. So I went from 90% transmittance, 10% gone, to 34% transmittance as I increased the concentration tenfold. Now, if I start there and increase the concentration a further tenfold, you can see there's another big step. I went basically all the way to like basically 98%. Now, what if I go a further tenfold? Well, now I'm going from almost all the light absorbed to almost all the light absorbed. And you really can't tell. So once things peg the meter, basically you can't tell if we've gotten more concentrated. So if all the peaks are strong, it might just be because we've basically pegged the meter. And you know, basically what's less than almost zero? Also almost zero. Right? So if you have something that's almost zero and I cut it by a factor of 10, I still have almost zero. That needle is still going to be on zero as far as I can tell. So that's really something to be aware of with IR. Most of the peaks you see, the relative strength is not going to be as easy to tell if you're dealing with thin film. Now, of course, the carbonyl peak, different functional groups will have slightly different frequencies, and a lot of that has to do with what's around the peak. The ketone, let's just call that your basic carbonyl peak. Let's just sort of decide that for our own purposes, we have to set a reference. Let's just say if we see absorbance between 1710 and 1720, you might presume it is just a Joe Vanilla carbonyl peak. And that can be taken down in frequency by conjugation. Conjugation, see, is going to spread the orbital system between these four carbons, and you kind of have this sort of more dotted line type system, you might imagine. This bond order is going to be slightly less than 2. As a result, that reduces the frequency of this, reduces the force constant, and so conjugation will lower the frequency of absorbance. Now, electron withdrawing groups, like a chloride or an oxygen, presuming they can't back donate electrons by resonance, if they're inductively withdrawing, what they're going to do is they're going to pull electrons off of the lone pairs of this oxygen toward the carbonyl. Another way to look at it is you could increase the positive character of this carbon, which is going to increase the electrostatic attraction between the carbon and the slightly negatively charged oxygen. Either way, we're lowering or tightening up that bond where it's going to be slightly shorter and it's going to be slightly stiffer. So electron withdrawing groups attached to a carbonyl are going to increase the frequency. And then amides are electron donating. They have a lone pair, and oxygen is much more, well, I shouldn't say much more, is significantly more electron withdrawn, or electron negative would be the word, than nitrogen. So I can imagine donating those electrons up toward oxygen by resonance, and this split charge structure is not as ridiculous as you might think, because of course oxygen loves electrons, and nitrogen's comfortable being positively charged. We see it's a base, it's positively charged in water when it accepts a proton. These are both situations we're comfortable writing, so that's a reasonable resonance contributor to write. So a certain percentage of this structure is going to look like this. This single bond here is actually going to be slightly double bond in character, and this double bond is going to be significantly single bond in character. As a result, we have quite a drop in the force constant there. So if we can donate into the carbonyl by resonance, we weaken the bond. If we withdraw electrons inductively, we'll strengthen the bond. And of course, if we share electrons, which is the same as donating, we weaken the bond as well. So keep all of this in mind as we discuss the functional groups that we're going to talk about. And yes, I did mean that extra E. I'm a poet. Don't judge me. So let's move on. Let's talk about ketones. So remember, we said that the vanilla carbonyl group, we're going to kind of set that in our minds as being around 17, 15 per centimeter. So there's hexanone. And there's a classic frequency for a ketone, and if we can compare this with others, and we'll see that move up and down as we change structure. One thing I want to point out is that there's other peaks that can be used to identify a ketone. See, we have this carbon-carbon asymmetric stretch. Generally, carbon-carbon stretches are not too informative, but of course there's a lot of dipole character to these because of the slightly charged carbon in the center. And so normally carbon-carbon stretches are really weak, but this one's a lot stronger. So we can look for something in the range of 1100 to 1200 to 1300 per centimeter, and that's often indicative of the carbon-carbon asymmetric stretch of a ketone. Of course, this whole region can often be quite busy, the fingerprint region, and difficult to pick anything but the strongest peaks out of and be sure of, so usually I would just stick with the idea that we'd look for the carbonyl peak there. Now, look right here. What do you see? That is an overtone peak. The overtone peak is the result of a doubling of this frequency right here. So basically it's a double transition. Instead of going from vibrational energy 0 to 1, we went from vibrational energy 0 straight to vibrational energy 2. Because remember, in the harmonic oscillator, such a orbital transition is forbidden, but we are not in a real harmonic oscillator. This is actually the Morse potential. It's a little more asymmetric, the shape of the bond's potential energy well compared to the harmonic oscillator. We discussed that in a previous presentation. So what's happening here is you can have a very unlikely transition. So forbidden just kind of means unlikely in organic chemistry. Notice that it is not exactly double. That should be 3436, but it's 3418. And that's, of course, because due to the asymmetry of the Morse potential, the vibrational energy levels get a little closer together the higher up we get. So that is a double jump, but it doesn't represent a perfect doubling of energy. So look for, if you see peaks in unexpected places, look for a really large peak at about half that frequency, and sometimes that would explain it for you. All right, so here's a bunch of carbonyls that we can, or ketones that we can explore. Let's look at the effect of conjugation. So this double bond is not conjugated. It's there, but it's not conjugated. So here is the CH2 stretches, always easy to spot. There's the carbon-carbon double bond, always easy to spot generally. There is our ketone peak, and you know what? It's pretty much exactly where we would expect, 1718, just like we'd had with the hexanone. So no surprises. The carbon-carbon double bond's exactly where we expect it to be. The CH2 peak on the alkene is exactly where we expect to be. Everything's looking good there. There's the asymmetric CC stretch in the ketone. I'm going to draw some lines. This line is down the 3000 line. Anything above it is alkene CH stretches. Anything below it is like the alkane CH stretches. And I've put a line right on the carbonyl frequency and a line right on the carbon-carbon asymmetric stretch frequency, just so that we can see how they change as we go to the next spectrum. So there is a phenyl group attached to our ketone now. Notice we still have alkene CH stretches, really, because of course we have sp2 carbons here, so we see those. If we see alkane CH stretches, because we have those. There's our big carbonyl peak, but notice it is lower in frequency, significantly lower in frequency. There's our overtone bands for a monosubstituted phenyl group, so we can spot that easily. And of course there's our bending vibrations for the phenyl group, which also would identify it as monosubstituted. Notice the change in the carbon-carbon single bond stretch. It's higher in frequency. So let's just go through the notes here. 1688, that is a lot lower than 1718, right? So, and of course a phenyl group is a significant amount of p orbital area to spread the electrons in this double bond over, so it's very effective at conjugating, so we expect to see a big difference there. Now, of course, if we conjugate, we're going to put some double bond character in the bond here on this side of the ketone, and that's going to stiffen things up, and so of course you can expect that the carbon-carbon asymmetric stretch gets stiffer and it gets a little higher in frequency. Here we see some characteristic carbon-carbon bond stretches that are characteristic of phenyl rings. There's usually a pair of them, one where we expect regular alkenes and one about 100 wave numbers lower, and that's pretty typical for a phenyl ring. So there's the frequency for the carbon-carbon single bond asymmetric stretch on either side of the ketone. As you can see, it's significantly higher than 1164. What if we put on two phenyl groups? Look at the numbers now. We're even lower because, of course, we're even more conjugated. We still see the benzene signals, and we'd expect to see those because, of course, we've got benzene. The carbon single bond stretch on either side of this, the carbon-carbon-carbon single bond stretch, is even stiffer because, of course, now both of these bonds have double bond character, so that lines up well with that. And there's our overtone region, not as clear in the previous case. Often the overtone region is a little muddled, but there's, of course, our out-of-plane bending for the phenyl groups, which can be a little easier to help us identify exactly what's going on. Notice we have no alkane CH stretches here, so that certainly tells us that it's all alkene, or in this case, phenyl groups. Now, those out-of-plane bending systems here tell us a lot about what we would expect to see for monosubstituted. That's very clear. There's monosubstituted. Both signals are there. That's very clear. And here's the out-of-plane bending for a terminal alkene, for basically a monosubstituted alkene. And again, and we talked about that in a previous presentation, and we can use those to sort of shore up those items right there. Ring size affects the frequency of carbon-carbon or carbon-oxygen double bonds or ketone bonds. Here is cyclohexanone, fairly unstrained ring. All the bond angles are pretty similar to what you'd expect in a regular alkane, and we have pretty much the same frequency for the stretch of the carbonyl group. If we go to a 5-membered ring, we're just a little higher in frequency. If we go to a 4-membered ring, we're even higher in frequency. So basically, as we go from 109 degrees down to basically 90 degrees here, we're increasing, we're using a p orbital here and a p orbital here. What we're doing is we're affecting the hybridization of the system by changing the bond angles. And as we go to higher, more intense angles here, we're basically going from sp2, and imagine the most extreme case would be a ketene where both of these bonds are parallel to each other, basically make a double bond straight out the other side, and that would turn everything to sp. So basically this double bond here is somewhere between sp2 and sp, and of course sp has a lot more s character. It's going to be a stiffer bond, so of course we're going up. If we go the opposite direction to a wider ring, we have a opposite effect, and of course a 7-member ring is not that much bigger than a 6-membered ring, so it's slight here, but bigger rings are going to reduce your frequency. Smaller rings, if the double bond is external to them, are going to increase your frequency. All right, so that's the notes on ketones. Esters. They're a pretty common carbonyl group. One thing right away you'll know about esters is that this is a classic example of what happens when you put an electron withdrawing group attached to a ketone. Oxygen is electron withdrawing. It inductively draws electrons toward it because it's electronegative. It's also very electron donating. If it can donate into an adjacent p orbital, it can form this kind of resonance contributor where you can actually, an oxygen, even though it is electron withdrawing by induction, actually stabilizes adjacent carbocations. So having an oxygen attached to a carbon that you want to make into a carbocation actually helps you do it. So that's an important thing in sugar chemistry and the formation of carbocations, and that's something you should review from organic chemistry. All of this kind of chemistry is something that you'll get from acid-catalyzed hydration of carbonyl groups and condensation reactions, ether formation. All these things could be explored or interpreted through this kind of resonance stabilization. So review your organic chemistry as to why oxygen actually stabilizes adjacent carbonyls. But if there's no p orbital to donate into, and there's nothing here, there is no empty p orbital here to donate into, the lone pairs in this oxygen can't donate, so all you have left is the inductive effect. So oxygen simultaneously always donates donates by resonance and withdraws inductively, and it's just a matter as to which effect is more important. Here, there is no donation by resonance, so there's only induction, so that oxygen is electron donating. Here, this oxygen is electron withdrawing. It always is, but it is sucking the electrons out of that carbon with a straw and dumping electrons back in with a bucket, so it is net electron donating. If it can donate into a p orbital, that lone pair will always be net donating. In esters, this oxygen here does not really have a strong resonance connection. There's a very tiny resonance contribution from this structure here. Why would you do this? Why would you create a split charge system? The Lewis rules say try to avoid that if you can. There's no reason to. Both of these oxygens are equally electronegative. Why would one want to take electrons from the other? They basically are tied in that tug of war. So this is possible, but it's an insignificant donator. There's a tiny bit of resonance donation, but not enough to overcome the electron withdrawing effect by induction. So since the resonance effect is so tiny, this oxygen is in fact net electron withdrawing from the carbonyl, and it's going to tighten up that bond there. So there's the notes on that. We're going to have a net withdrawal away from the carbon, and that's going to increase our bond strength in the carbonyl group. Let's back that up with some chemistry. This is the pKa value for a benzoic acid, 4.21. So it's a moderately weak acid, basically. And what would the effect of an electron withdrawing group be? Well, let's put an oxygen on in the meta position. In the meta position, it cannot donate by resonance up to that oxygen there. It can't add any electron density to where my reaction center is, but it can withdraw inductively from the phenyl ring, and if there's less electrons in the phenyl ring, then obviously this will feel that lower electron density. It's easier to make a base out of this. Basically, this is a stronger acid would be the better word to put it. It gives up its proton more easily because we can make that negative charge. That negative charge is being stabilized by the electron withdrawing effect from induction, and that is not being swamped by any kind of resonance donation. The opposite effect is to put it in the para position. In the para position, I can push here, push here, push here, and I can push that double bond up into the single bond and this on up into there. Or you could imagine it just all collecting electron density here and this feeling the inductive field effect of that. In either way you want to imagine it, I can increase the electron density in the area of this, which makes this less likely to form. And look, it is not as strong of an acid. So remember, low pKa's means strong acids. High pKa's, you're moving toward bases, right? So in this particular case here, I am doing an electron donation into something that is negatively charged at the product, so I'm destabilizing the product. Here I'm doing withdrawal in something that's negatively charged as the product, and I'm stabilizing the product. Stabilizing a negatively charged product coming from neutral helps. Destabilizing a negatively charged product coming from neutral doesn't help. So there's proof. When oxygen cannot donate by resonance, it is electron withdrawing. When oxygen can donate by resonance, it is electron donating. So those are the notes on that point. So we'll see a lot more of this. You'll see a lot more of this concept in advanced organic chemistry and physical organic chemistry later on. But you might want to also investigate a review of organic chemistry of how the methoxy group is an orthopara director in electrophilic addition to benzene rings. And that has a lot to do with this electron donating character as well. So you'll review all of this concept if you review your organic chemistry about electrophilic addition to benzene rings. All right, so let's examine esters a little more deeply. Here is a typical ester, and one thing you'll notice right away is that the frequency is pretty high. 1740, 1745, those are pretty typical frequencies to see for esters. Here we've got it pretty much close to 1740. Now another thing an ester has is a carbon-oxygen single bond, and that's going to show up quite clearly around in the neighborhood of 1200. 1100 to 1200, and we'll often see a second CO stretch because there's a couple of modes by which this can stretch, and it's often weaker and difficult to spot. So I mostly go by if you see a single really strong band in the range of 1100, 1200, that sort of like neighborhood there, sometimes size 1300, that's going to be indicative of a CO single bond. If we've got a CO single bond and a carbonyl, I'm guessing ester, especially if the frequency is kind of high like that. All right, so let's sort of talk about the consequences of conjugation. As with ketones, if I conjugate, there's a double bond there conjugated to the single bond, I lower the frequency from 1740-ish back down to 1726. So that's I lowered the frequency. And there's the other signals we'd expect to see with this kind of thing, the CH on the alkene. There's the CO stretch, nice big strong peak there. Now, what if I put the vinyl group on the other side of the oxygen? Not here, conjugated with the carbonyl, but here, conjugated with the lone pair on that oxygen. In that case, I greatly increase the frequency from 1740-ish to 1764. So why would that happen? Well, I've actually helped that oxygen become more electron withdrawing. Let's explore. Here is the idea of the oxygen doing some resonance donation toward the oxygen on the carbonyl group. So here I'm pushing electrons toward the carbonyl group. And I said that was a pretty minor contributor by resonance. And it is. It's minor. These electrons pushing up here. But it is there. What the vinyl group does is give the oxygen another option. So now this oxygen has two suitors, two groups calling for its attention. So its ability to donate by resonance to this oxygen is reduced because it's also donating to the other end of the carbon chain. And basically all it does is, instead of all of the electron density, what little bit gets donated up here, now we're sharing it. So I've made the oxygen effectively more electron withdrawing, not by increasing its induction, but by further reducing the countering resonance donation. So it's always withdrawing, and in this case it was slightly donating, and now it's even less donating. The withdrawing was always there, so now it's even more withdrawing. So that sort of explains how a vinyl group off of the oxygen, or any kind of conjugation off of the oxygen of a carbonyl, will actually increase the frequency. Now, here we have ester rings inside esters inside a ring, and that's called a lactone. And this is a good time to review your nomenclature from organic chemistry of these compounds. And I just ask you, what's a lactam? Any guesses? So check out your nomenclature and figure out what a lactam is. I might ask. So here is a 7-membered ring and a 6-membered ring and a 5-membered ring for esters. Notice how the 6-membered ring, I should say here, is a pretty typical around 1740 frequency. A bigger ring lowers the frequency. A smaller ring increases the frequency, just like we saw with ketones, and for exactly the same reasons. Amides. Now that's an important group, very important group in proteins and biochemistry. A great electron example of electron distribution, so it's an important group. Now, amides have a good deal of double bond character in the carbon-nitrogen bond here, and that is because oxygen is more electronegative than nitrogen, and as a result, this contributor here is a pretty significant contributor. It's about 25% of the care. If you cross your eyes and blur these two structures and get this sort of distributed structure, 25% of it resembles this structure. So there's a 25% of a negative charge here, 25% of a positive charge there. So as a result, you can expect that this single bond or this double bond here has a lot of single bond character because there's like 25% of that there. I would expect a amide to have a lower frequency than a ketone because the bond order is less than 2. Let's see if that bears out in the experimental results. Here's some other sort of results from the literature that sort of back up my example. The sort of energy it takes to rotate this oxygen-carbon bond here, which is just a CH3 group, you'd expect this would spin freely, is 8 kilojoules per mole. And that's just sort of the steric clash of this, one of these hydrogens lining up with that oxygen, if they line up in a gauche or an occluded formation. So basically, as I spin this, I'm constantly going through an 8 kilojoule per mole barrier. And we know that that would spin freely. So obviously, 8 kilojoules per mole does not prevent things from spinning freely. That's just, we're at room temperature. There's more than enough energy to enable that to spin freely. Notice how the energy for rotation of this bond is slightly higher because there is that tiny bit of resonance donation, but not really. So this bond spins freely too. 812 is not that much bigger than 8. 85, however, is 10 times bigger than 8. That's a whole order of magnitude greater of energy required to rotate the nitrogen-carbon single bond in an amide, indicating that, of course, there's a lot of double bond character, and amides are famous for resisting rotation. You can rotate them. There is a rate at which they rotate at room temperature, but it's not fast. because of this huge barrier. So there's proof that we have that electron donation in amides, but not in esters. And of course, if you have a true double bond, it's not going to rotate at all. 270 kilojoules per mole is that's on the order of magnitude of breaking a carbon-carbon single bond. So you're not really going to be able to rotate that bond at room temperature. All right, so let's look at some examples. So here's a typical amide, and if we look at the frequency there, 1750 being our ketone baseline, 1660, a lot lower. That is a lot lower. Other features that you'll notice is that the NH peak here, there's two of them, because just like in amine, there's two peaks when there's two hydrogens. But this is a really intense absorption band. With amines, we had little low absorption bands here, and this is really intense. So if you've got something that looks like a primary amine, but it's super intense, I'm thinking amide. And then I see a low carbonyl peak, now I'm really thinking amide. There's a carbon-nitrogen stretch that can sometimes be picked out, but it's usually not too strong, usually lost in the crowd. I would go with the amide peak. Amide peaks often have this little sort of split at the top or a little bit of doubling, and often that has to do with the carbonyl peak combining with the NH bending frequency. So anyway, just a little kind of tick there also helps you spot the fact that it's an amide. Now, here is a substituted amide. Notice only one NH peak. Still, again, fairly strong. So that could be a primary amine, or not primary amine, a secondary amine, or it could be a substituted amide. Since it's so strong, I'm thinking substituted amide. And of course, boom, there's the CO stretch again on the low side. And then this spectrum is kind of complicated by some overtone bands from this NH bending here. That's like just almost double that. So don't be fooled by that. You'll get that with experience. But really what slams this as an amide is the low frequency for the carbonyl and the obvious NH bond. Now things get a little more difficult to interpret when you're talking about tri-substituted amides because there is no clear NH stretch here to sort of say, hey, there's an amine present. All we have is a low carbonyl stretching frequency. But of course you'll know that there's a nitrogen in there from mass spec. So when you see the low frequency, I would start to suspect that that carbonyl has an amide on it. Hopefully some NMR will be there to really shore things up for you. Now, conjugation in amides doesn't have the same level of influence that it does in ketones and esters, and that's because the electrons are already distributed. I mean, so there's a small effect, but it's not huge because, of course, we had distributed electrons here. Now, of course, the electrons can go the other way. So instead of being 1650, we're a little bit higher, maybe 1660 in this case, because instead of this just being able to donate electrons up toward the oxygen, it is pushing them that way. But really, you've gone from a distributed system to a distributed system, so it's not like it's apples and oranges, right? Not a huge difference. There's the NH peak. There's the NH peak again, nice and strong, and we're seeing it clearly. So here's conjugation off the other carbon group. Do you think that would lower the frequency? Not so much, not really. Again, we've gone from a distributed system to a distributed system, so not a huge bit. So conjugation is not going to have a huge effect in amides, but excuse me, it is going to, it has a tiny effect, nothing to need to worry about. Here we have two hydrogens, and there we see the two NH peaks, nice and clear. Again, just like in the case of ketones, just like in the case of esters, ring size matters, and small rings will increase the frequency of an external double bond, and large rings will decrease the frequency of an external double bond. So you know that already. All right, so what about other options? Well, acyl chlorides are nice reactive reagents which you can use to make esters and amides. And what is the effect of that chloride group? Well, it's really electron withdrawing. As a result, I would expect it to strengthen that carbonyl group quite a bit, and look, it does. With chlorine, we can often see the carbon-chlorine stretch there as well. And those are things you can look for when you're trying to sort things out. But you'll know there's a chlorine there from the mass spec. You'll see the really high frequency for the carbonyl. I don't think you'll have any trouble identifying that as a acyl chloride. And hydrides are easy to spot because of this extreme doubling of the carbonyl group. There's two ketones there, or not ketones, there's two carbonyl groups there on either side of the oxygen of the anhydride group. And as a result, there's two possible combinations of their stretches. Their stretches could combine by going in the same direction, or they could subtract by going in opposite directions. That's going to result in two energies. So it's a lot like the idea of molecular orbitals combining. If I had two molecular orbitals, let's say that that's a fairly electron withdrawing group here. Let's say that, imagine that the frequency of both carbonyls is actually 1785, but then so there's 1785 and 1785, but they're next to each other, they're lined up with each other, the orbitals combine, and you end up with a splitting of energy, and one's a little higher and one's a little lower. So that's a combination of the quantum energy levels leading to that split. So if you see basically two strong carbonyl peaks, one really high, the other also fairly high, that is going to be an anhydride. So look for that. Look for the split carbonyl peak and the fact that it's on the high end. And you'll be pretty sure you've got an anhydride. And of course, there's a carbon-oxygen single bond there to help you spot all that. Now, carboxylic acids. They're an interesting fish. You'd expect to see an OH peak. Where is it? I don't see it here. Oh, look. There it is. The OH peak is, in fact, underneath here. The carbonyl peak is a little lower. We'll explain that in a second. A lot of this has to do with the fact that this OH stretch is a lot lower and the fact that the carbonyl stretch is slightly lower than you'd expect has to do with hydrogen bonding. In a neat liquid, which is what most IRs are that you get from online databases, it's generally a neat cast on a salt crystal. You're going to have a pure liquid. Carboxylic acid is basically all going to hydrogen bond to make these dimers. Now, notice how if I'm donating some electron density from this oxygen into the antibonding orbital of this hydrogen to create that hydrogen bond, then I'm going to be weakening this OH bond. So of course the OH stretching frequency is going to drop and it's going to end up under my CH stretching frequency. And of course if I'm donating some electron density out of this oxygen into this hydrogen to make that hydrogen bond, I am decreasing the strength of this carbon-oxygen double bond just a bit, tiny bit, and we're a little lower than you would have in the case of a ketone. Here's a more extreme case with a carboxylic acid. Over here we see a really large sort of OH-like absorption, but it is solidly underneath all of the CH stretches, which makes the CH stretching region kind of hard to interpret. But if you draw your line down 3000, you see detail here above 3000, so you know you've got an alkene. Of course, we see the carbon-carbon double bond stretch there, so again, got an alkene. There's CO stretches in carboxylic acids. You see it there. You see it in this one. You sometimes see the OH out of plane bending, which would be bending here in this hydrogen bonded situation. But that's not too diagnostic because often the fingerprint region is pretty busy. I would concentrate on the fact that the OH stretch is broad, enormously broad, and significantly lower in frequency than in alcohols. That's the diagnostic one right there for acid peaks. And then your carbonyl stretch is a little on the low side, but really the slam dunk is look where this massive OH peak is. Aldehydes. Now there's an example of what happens when we sort of reverse the idea of an electron donating group. A CH3 group is slightly electron donating. Believe it or not, CH3 groups are slightly electron donating. Think about it. If you substitute hydrogens on a carbon with CH3 groups, you would stabilize any sort of cationic center on that carbon. So we know that alkyl substitutions stabilize carbocations. Now, so they must be electron donating. Hydrogen is not as electron donating, or well, I mean, let's call that the standard. It's the zero. Everything is more electron donating than hydrogen or less electron donating than hydrogen. Well, CH3 groups are more electron donating than hydrogen. So substituting a CH3 group for a hydrogen is in fact making things a little more electron donating, if you will, or less electron withdrawing. So remember, electron withdrawing groups increase the frequency of the OH group. So what do you think And what do you think going from something that was electron donating to something that's not electron donating will do? That's the same as adding some electron withdrawing character, isn't it? As a result, you can expect that since we've gone from something that donated a little bit to something that doesn't donate at all, we have basically gone to a lower electron density at this carbon here, which increases the strength of that double bond. So look, a little higher than a ketone. But what's really diagnostic of an aldehyde is the fact that this stretch here for the H is coupled with the ketone stretch, anyway, not the ketone stretch, but with other resonances that generally don't usually show up in IR. They're sort of what they call a Fermi resonance situation. And what we see here is resonances that really you wouldn't have seen otherwise get energy donated into them from this carbonyl group. So there's a lot of like CH stretching modes that never show up. But suddenly this carbonyl group is able to donate because it's directly connected to the hydrogen. It's not like in some other part of the molecule. So stretching modes that wouldn't have shown up actually do show up here. And as a result, the CH stretch, we see more than one version of the CH stretch. I call this the aldehyde fangs. If you see these like two really strong peaks in the CH region, fangs, fang, fang here. If you see the aldehyde fangs then and a carbonyl group there, then you're pretty sure you have an aldehyde. Of course, things aren't always so cut and dried. So we can take those fangs, we can go over here and look at this sort of cyclohexane carboxaldehyde, and there's the fangs right there. But because we've got a lot of CH stretch going on here we only had the methyl group. We've got a lot of CH stretching here. There's a lot of detail in the CH stretching region. One of those fangs is kind of buried. But that's okay. We generally don't expect to see CH stretches this low, way down around 2740. We generally expect CH stretches to be 2850 to 2950, and this is at least 100 lower than that. So if you see a fairly strong CH stretch and it's a lot lower than you thought, and then you can kind of look at it and sort of convince yourself that there might be a second one in the cloud, then again, aldehyde fangs, they're in there. We're only seeing one of them. He's only half smiling, but there's the fangs. And of course, there's a slightly high carbonyl group here. So those are some other carbonyl groups that you can kind of get to know as you go through and look at your correlation tables and sort of practice problems in your textbook and any other problems that are assigned. You're going to get to know all of these. And just remember, the way I like to think of it is, I'll just give a little summary here. We looked at just a few examples, but we've kind of sort of seen some general principles here. So here's just some of the things we've learned. And we haven't learned that much, but we will be able to use all of it. If we just said that we consider a carbonyl to be a 1715 per centimeter frequency, and that was sort of what we had for ketones, then we just always think about what increases that or what decreases it. And conjugation decreases the frequency. And putting electron withdrawing groups or making electron groups less electron donating, either way, going to a more electron withdrawing character increases the frequency. And that's pretty much, that's everything. That's everything we need to know. And that explains every observation. So here we have a ketone, and we expect to see the ketone stretch at 1715. There's no, of course, carbon-oxygen single bond in a ketone. Here we have an ester, a little higher, around 1740, typical frequency, and we expect to see a carbon-oxygen single bond, a good strong peak there, somewhere between 1100 and 1300. With amides, a lot lower for the CO stretch, and we look for NH stretches up above 3200 there, basically in the range where we look for OH stretches. Acyl chlorides, we expect to see these higher peaks because the chlorine is very electron withdrawing, and again, so in the neighborhood of 1800, a lot higher. So if you see this really high peak, a single high peak, an acyl chloride of some kind would be a good bet to go for. Of course, there's lots of special situations in IR that could result in a peak that high. You could have, for example, a four-membered ring in a ketone. If your mass spec says there's a chlorine in there, I'd go with acyl chloride. Acetic anhydride, again, very high peak because, of course, both those carbonyls are now attached to a very electron-withdrawing oxygen, and then split a little higher and a little lower by the fact that the two frequencies are combining. And you'll expect to see a CO peak in that, of course. Then you have the carboxylic acid. With that, you expect to see this really broad, much lower in frequency than expected OH peak. Sometimes it's so broad it's hard to spot. You think it's just a lump or a bad spectrum, but keep an open mind. And again, the It's not a tremendously lower signal, but it is a little lower than ketones. So if you're slightly on the low side, you've got a carbon-oxygen single bond, and you have this sort of big lump messing up your whole alkane stretch region, carboxylic acid. Aldehydes have the fangs, look for the fangs, and a slightly higher frequency. And all of that compares to just a regular alkene double bond. The alkene double bonds are 1650. Remember, carbonyls have a slightly higher force constant, so a vanilla carbonyl is 1715, basically 65 per centimeter higher, and then that force constant is increased by electron withdrawing groups and decreased by conjugation. So let's look at a little problem here. So here's two molecules, and they've got fairly similar CO stretching frequencies. Which one's an ester and which one's a ketone? Okay, so let's think here. Why would they have the same stretching frequencies if one's an ester and one's a ketone? Well, maybe there's a reason that that ketone is slightly higher in frequency than it should be. Or maybe there's a reason that that ester is slightly lower in frequency than it should be. Can you remember what increases the frequency of vibration in ketones and decreases the frequency of vibration in esters? That would be useful in solving this problem. So one thing I notice in this particular spectrum right here is that there's a carbon-carbon double bond, and I can see a little detail above 3000. Sometimes it's not very strong, but there it is, and that's an alkene CH stretch. I see the exact same thing here and the exact same thing here. So I know there's an alkene in both of these. I see CO stretch here. I don't see as strong a signal here. So, and I know one's a ketone and one's an ester. So if that's the ester, because it's got the CO stretch, then that's the ketone. Can we confirm that? Well, let's look at the other evidence that's here. Let's draw our line. Wow, they are both pretty similar. So if this is the ester, and it's coming out a bit on the low side for an ester, then I would bet that it's conjugated with the double bond. And if this is a ketone, and it hasn't been lowered, then I would say it's not conjugated with the double bond. What do you think? And the CO stretch there, we see it here, and we don't see a strong signal here. This is pretty much not strong enough to be a CO bond, so one of many other stretching results. So one thing we could do to try and shore up the idea that that was weaker is go to a less concentrated system. All right, so let's dissolve this in chloroform rather than sticking with the thin film IR here. And look what happened in chloroform. Our carbonyl peak is still pegging the meter in both because it's incredibly strong. But instead of this being 99.99% transmittance, maybe it's just 99.9% transmittance now. As a result, we have reduced the strength of the signals of things that aren't very strong. Look at this. All of these signals here have dropped quite a lot in intensity relative to the carbonyl. But here, these sort of signals here have dropped in intensity, but the strongest ones are still pretty strong. You know, the difference between 90, you're already 90% and you're significantly attenuated, you're still pretty strong. So that is definitely a carbon-oxygen stretch. And here we saw it go from 70%, and it dropped quite a bit right down to like 40% or 30% transmittance there. So relative to the carbonyl peak, that's not very strong. Relative to the carbonyl peak, that is still strong. So I know that's a strong peak, and that CO needs to be strong. So that is a CO peak. So I've got a carbon-oxygen peak here. I've got the carbonyl stretch. It's a little lower than I expect. I think that that's a conjugated system. Let's take the mass here. The rule of 13 gives me C8H18, but that's only 1 degree of unsaturation. I have a carbonyl group, and I have an alkene. I need 2 degrees of unsaturation. So let's add 1 oxygen, which increases our degrees of unsaturation by 1. A second one, there gives me my 2 degrees of unsaturation. If I've got 2 oxygens, again, I suspect ester. That really kind of backs up the idea of an ester. So let's see what we might draw. If we've got 2 oxygens and ester's a possibility, we've got the CO stretch, I'm feeling pretty good. I'm feeling pretty good that that is a conjugated ester of some kind. This is a possible structure. Is the CH3 group here? Is it here? Well, we could look at bending vibrations in this neighborhood here. We can look at the relative strength of that, and you could sort that out. But I'm pretty sure that there's a double bond conjugated with an ester. Are the alkyl carbons in the right place? Only NMR is going to tell for sure, in my opinion. But you can get an idea that if you look at this in detail, you can sort of back up the idea that it is a geminal substituted double bond. In this particular case, what might that be with this molecular formula right here? Well, if rule of 13 gives us this formula, C7H14 with 1 degree of unsaturation, I know there's at least 2. Adding an oxygen gets me there. So 1 oxygen, 1 ketone. I don't think it's conjugated, but I know there's an alkene. It's a nice strong terminal alkene. We don't see a strong CO peak, so I don't think there's an ester here. So I don't think it's conjugated. So maybe it's this, maybe it's this. All you want to do is draw something that's not conjugated. And again, we'll turn to the NMR and that would settle that hash. So those are the actual compounds that I got from the Aldehyde spectral database to generate these. So these, this is 5-hexene 2-one. So let's see, 1, 2, 3. Oh, not that one. 1, 2. There we go. 2-one. So there we go. So there is 5-hexene 2-one. You have to put the 2 in the lowest position here because it's a ketone, and the lowest number has to be associated with the defining group. So it's a 2 ketone. So there's the 5 number on the alkene. So that's how you can use IR to sort of really identify the functional groups, identify some features about them, conjugated, not conjugated, electron withdrawing groups attached. You can use all of that to try and solve these puzzles. So here's a question for you. There's ethyl allyl ether. This is the structure here. It's not conjugated. And here is this ethyl vinyl ether. It is conjugated. Can we make sense of the observations below? I'm looking at the carbon double bond. It's about where I expect, 1650. Here I'm looking at the carbon-carbon double bond. It's a much stronger signal, but it's a little lower, 1640. Why is that? Here I've got the carbon-oxygen stretch, typical region there, 1100. Here I've got the carbon-oxygen stretch, also a typical place, but it's a lot higher, 1200. Why is this fact that this is conjugated? Why did it lower the frequency of the double bond and raise the frequency of the single bond so much? So as you answer that for yourselves, consider enolates, consider how vinyl ethers are electron rich and good nucleophiles, and sort of review your organic chemistry with an idea of nucleophilic double bonds. And usually that's, of course, because they've got an oxygen attached to them. Here we have an enol ether. Think about the nature of enol ethers compared to this, and think about, as you think about why this double bond is so nucleophilic because of this oxygen, think about the nature of that single bond. Is it really all single? Think about the nature of that double bond. Is it really all the way to double when we're sort of imagining the electronic structure of an enol ether compared to something that is just a regular alkene? So again, review your organic chemistry, use what you know about organic chemistry and the reactivity of systems, and that could explain this for you. So I invite you to talk about that with your friends. Ask me if you can't come up with an answer. All right, so that's the nature of the carbonyl group. It's a really obvious group to find. It's a really easy group to identify. So if you can identify carbonyl groups quickly, you will be able to excel in this course. So good luck to you.